dear student, today we will start to discuss on the fourth module. The fourth module name is environmental pollution and water chemistry. So these two words are very familiar to you because you have this word environment as well as pollution, including of this water. So these are the look like of our basic needs. So those in this word, what we can try to clarify is in the engineering chemistry. So already you know it something. So in that very elaborate discussions of the terms of environmental pollutions, including of the water chemistry. So in first part is environmental pollution, second part is water chemistry. In these two parts, I will select first the second part is water chemistry. So already I have studied up to the period level of the structure of water. So for this what are its bonds, characteristic features, anomalous properties, all other you have studied. But in this +2 level, we have not studied what we are going to discuss on these topics. In this water chemistry, we will going to discuss how much a percentage of water is available to us, and including of what are its impurities, whether it is dissolved or undissolved, and how much of the impurities are there, what are its unit, how to measure it, followed by including let me decide it is using for some purposes, it is not using to anything also, any purposes, though we call it as a sewage or wastewater. So for this also it is starting of measuring or find out of its COD, BOD, including of any total TDS, total dissolved salts, what are its individual salts, what are those methods. Finally, we can take this image, how to it is we can converting into, purify into this drinking water or 0 ppm water. PM means parts per million. So 0 ppm, even not even 1 milligram is also not dissolved. That water we can call it as a purest water, that is distilled water, double distilled water. The example is rainwater is pure water, purest water is a double distilled water. Its the impurity is 0 ppm. So what is this? So far we can going to discuss these topics in the water chemistry, of course. So that first we will start. So already we know about of this, the number of other planets. Only our Earth is having 3/4 of hydrosphere and 1/4 of lithosphere. It means 71% of water has covered the surface of the earth. We can call it as lithosphere. Remaining 29% is not covered the earth's surface. We can call it as a lithosphere. Out of this 71%, so seas, oceans, rivers, of course, other oceans, including of these some lagoons, all those things are there. Still, so in this 71%, out of this, suppose we can raise us into the 100%. Out of the 100% of water, only 97% is salt water. If you want to drink this salt water, not possible. Why? Too much of salt is there. If you want to use, this example is sea water, ocean water. We completely too much of maximum salts more than 1000 ppm is dissolved. It is also unfilled. It dissolved only the salt. So you can remove all the 1000 ppm of salts from that. Automatically it is, we can call it as a purest water or soft water or drinking water. It can use for all the purposes. So far, out of this salt water is there 97%. It is, we are unable to use it. It is not, its availability also not using for any purpose until we will remove of all these salts. So it is there. Look like a physiological deficiencies. Water is this, we cannot use directly because it is So too much of impurities is there. As the same way, remaining 3% of sweet water, potable water, drinking water is there. Only 3% is there for sweet soft water. Out of these 3%, 2% is located near the polar region, near the Antarctica region. It has located, situated. So only 1% is available to us. So far, we always take care about of the very much important resource in the basic needs, food and water. That is, of course, it is water. The 1% is available to the human beings. In that 1%, 0.5% is on the surface. We can call it as a surface water. So remaining 0.5% is in the earth. We can call it as a underground water. We can pumping it through artesian bodies or through artesian well or even normal wells, and some other techniques we can bore it and we can get it 0.5%. That is also it is containing alkalinities. But remaining 0.5% is available in the form of rain, in the form of cloud, in the form of river, in the form of pond, in the form of ditches. All those of course are there. So very less impurities are there. Below 200 ppm of impurities are there. That water is fit for drinking and as well as other purposes. So far, now you are very clear about of 100% of water, 97% of water is there. Without purifying, we could not use anything. Remaining 3% is sweet water, 2% is not available to us. 1% is available to us. 0.5 is easily we can get it. Remaining 0.5% we can discharging of our energy. So wasting of our energy to get off this drinking water and other purposes of water. So far we can give more precious about of water. So how much of water is available to the human beings? Only 1%. That water we can call it as sweet water or soft water, using for all purposes. Now, so for this we are using the term pure water, soft water, because it is using for all. Suppose its ppm, its hardness, any total dissolved salt is more than 300 ppm, it is not fit for drinking. More than 400 ppm, it is not fit for washing also. More than 500 ppm, it is 500 to 600, not fit for agriculture also. More than 700 ppm, not fit for any of the some building construction also. Of course, it is reaching 1000 ppm, you call it as sewage. So far, you taking the water sample, you test it, what is its hardness. That hardness you can calculate it. So immediately, how much of the salt, total salt is dissolved in that, it is expressed in our first experiment, determination of the total hardness of the given water sample. As the same way, so here we can taking this. So before we go into assessing of total only the dissolved salt, other things are there. Undissolved forms are also there. Suppose not only dissolved salt is there, dissolved gases are also in the water is dissolved. So for dissolved salt, dissolved impurities, suspension impurities, colloidal impurities, followed by some of these what is we can call it as microbial impurities. There are 4 types of the impurities we can go into estimate, we can go into assessing to those or classified to those. In first we will consideration of the point is dissolved impurities. In the dissolved impurities, some salts also dissolved, some gases also dissolved. For example, what are the salts? Sodium chloride you can add to the water, completely. Copper chloride, copper sulfate, magnesium chloride, magnesium sulfate, magnesium carbonate, sodium sulfate, sodium hydroxide. You can add any of the salts to that, immediately having the capacity to dissolve almost all the salts. So for this character we can call it as universal property of the water. So what we can call it as universal solvent. It can dissolve almost all types of the salts. As the same way, it is having the capacity of dissolve some gases also. What are those gases? So what are the purity of water? How can you say? You can taking any ml of sample water, it definitely containing only the two molecules or two atoms of hydrogen and combination with the one atom of oxygen. We can call it as molecular formula H2O. Other than this, anything is there, we can call it as impurities. So far, other than this, excess of hydrogen is there, that is also impurity. Excess of oxygen is there, that is also its impurity. Any of the percentages of carbon dioxide is also there, that is dissolved gases. Sulfur dioxide is there, that is also dissolved gases. Any other H2S, hydrogen sulfide gas is there, that is also impurity. Chloride gas is there, fluoride gas is there. So any of the gases are also dissolved, that is we can call it as dissolved gases. You dissolved salts, oh yes, both of these are under this first category, dissolved salts and dissolved salts and dissolved gases. So second type of impurities we can mention as a colloidal particles. Already you know about of these. What are these? Instead of completely dissolved, so it can dispersing in the sizes of the impurities are, so 1 nanometer to 100 nanometer size of the particles, not the dissolved gases. It is a sort of dispersed salts, dispersed things. So it is not possible to dissolve, because for dissolved more than 10 to the minus 10 meter or 11 meter or 12 meters. So below to that, it is not dissolved, it is dispersed. So we can call it as a colloidal impurities. Colloidal impurities are any dust particles. It is dissolved, it is dispersed in the from quarries or from any microorganisms, any silts, sands, soil particles, any some small debris. We cannot filter paper also, but it is not dissolved. So those type of the impurities we can call it as a colloidal impurities. So second type is also over. So third type is we can call it as something. The third impurity is suspensions. So already what you can know it as, it is not possible to dissolve also, or not possible to, it is colloidal molecules also. So more to that side, 1 to 100 nanometer, more to that side, not possible to either dissolve or colloidal particles. So that is we can call it as a suspensions. So these suspensions are examples of small stones, so big sands, silts, clay, any of the part of the rocks, any debris, wastage sizes more than 100 nanometers. More than 100 nanometers, we can call it as a suspensions. It is not floating also, or not dissolved also, including of any of the twigs, portion of the leaf, or any humus, or any organic not dissolved in the water. Might be it is floating, we can remove it also. So it is not floating, so it is the heavy molecules, it is polymers. It is totally, instead of floating or dissolving, it is settled down. It is near the bottom, so it is settled down if the water molecules are floating also. Those type of the impurities, we can call it as a suspension impurities. The fourth type of the impurities is to water is the biological impurities. The name itself indicates biology means related to the life. Those are whether it is amoeba are there, or knockout's are there, or even bacteria are there, or including of any viruses are there, or any fungi are there. So totally these are the microbes present in the water. All these four types is also there, or any one type is also there. So that is unfit for drinking purposes. So only we can accept either little bit of these salts or any other we can adding of these acids, acids, salts, and any other gases are there. Maximum is 200 ppm. That is, we can call it as a TDS, total dissolved salts. Anything it is we can dissolve. Maximum is 200. That is more to that we cannot using for drinking. Less to that we can test all those things. What are the percentage? How much of 200 ppm? How much of ppm of calcium carbonate? How much of ppm of magnesium carbonate? What you can detect in the lab in the experiment number 1. So in that total hardness, here, so in that how much of percentage of calcium salt is there, magnesium salt is there, potassium salt is there, iron salt is there, any other salts also, many metal salts that should be dissolved, or it is in the form of colloidal forms also. How much is dissolved, we can totally estimate, then we can label the given water sample. It is fit for this, it is fit for this, it is fit for this. Too much of impurities, not fit for anything, we call it as a wastewater, or we can call it as a seaweed. So far, the introduction of this water impurities, these 4 types, we can go into assess. For this, for drinking purposes, we are getting the water is below 200 ppm. Suppose for this boiler purposes, how much is there? Only 2 ppm. So what you can know about of this until today of itself? The boiler, it is you are getting the hot water from the boiler, you can pass the electricity. What is this boiler? It is a cylinder. Look like say it is a cylinder. Both the sides it has covered, and it is used to get the hot water. That is, we are using the boiler in houses. So we are using the boiler in factories. So we are using those. It is a compact disk type, too much big size, 1000 liter or 2000 liters capacities. Look like of overhead tanks. Look like of overhead tanks. We are passing the water and produce the steam. Passing the water, you heat the boiler, and it should not produce the water, it should produce the steam for generate the electricity or to run the factories. So that type of the boiler is also there. So it can use the water, we can call it as a boiler feeding water. So in this boiler feeding water, below 2 ppm, so means 1000 ppm means 1 gram of total salt, all salts dissolved in 1 liter, we can call it as a 1000 ppm. In that 1 milligram is dissolved, we can call it as a 1 ppm. Maximum is using for this boiler feeding water is 2 ppm of salts, whether it is iron or copper or sodium, calcium or any other salts, even including fluorine, chlorine, all the anion cations, all this total maximum is 2 ppm of impurities of dissolved TDS. More to that, it is not fit for boiler feeding water. So far, so this below 2 ppm of boiler feeding water, purest water, we can use to produce the steam for generation of the power or to run the industries. That water we can call it as a boiler feeding water. So in this boiler feeding water, almost all we can use 0 ppm waters we can use it. If it is at the time of carrying or pumping or discharging to anywhere or into the units or into the overhead tanks, at that time, so automatically 1 ppm or 2 ppm impurities, and we can get it. If more to that, frequently we will test its hardness, test the TDS. If it is there, we can externally treat it. Externally treating of add EDTA or to remove any of the salts are there, we can remove it. Afterwards, we can fill the water to the boiler to generate the steam. We can call it as a boiler feeding water. So why are you using of this? To generate the steam. For what purpose of the steam? Whether it is a steam, it can generate the electricity of the factories, it can rotate the main axle of the generator, or it can use to this some other change the energy into this mechanical energy, or we can using of sterilizations of any medical field instruments for the operation purposes, we can use it. So like this, too much of heat is generated in the steam. The steam is carrying too much of heat along with this steam. So far, we can give the priority to the water for generation of the steam. So far, for boiler feeding water, below 2 ppm of dissolved salts, water we can use it. Better we can get plenty of the steam and plenty of energy is also conversion. The heating charge we can also use it for some other purposes. So for what is the name boiler feeding water? The purest water is used to produce the steam for the purpose of power generation or to run the industries or to run any other purposes. That is water we can call it as a boiler feeding water. So what is its ppm is? Below 2 ppm of its TDS or oddness is there. Suppose little bit more is there. If from that no advantages we have taken, only disadvantages are there. So far, so what is there below, above this 2 ppm is there. So stop that. Yeah. In this, any more than 2 ppm is there. We can test it also. After tested also, some of the impurities is added. So we can start the boiling of this generator boiler. So we can producing of the steam. So what is the boiling point of water is 100 degrees centigrade. Of course, in that water is steam is generated, that is passing into this its valve pipe, and where it is we can having the convenience to pass, it will go. But any impurities are there, that impurities boiling and melting point is not 100 degrees centigrade. So far it is not passing with the steam. So it is when we are going to the using of every day 100 liters of water for making into a steam. So tomorrow is 100 liters, day after tomorrow is 100 liters, like that. And we can one day you can increasing of 200 liters also. Anyway, you can convert the water into the steam. At the time, how much of quantity of water is converting into the steam, that much of salt is the dissolved water is not evaporated with the steam. So that is one or other ways it can floating in the water because it is forming into the steam. Finally, thin scale is formed and it is hard and attached and adherent and attached or pasted on the inner wall of the boiler. That it is undissolved salts is pasted adherently on the inner wall of the boiler. We can call it as a scale. You remember this, not your measurement scale. It is a chemical process. The example is, if you can take 100 grams of, you take in two beakers containing 100 ml of water, another beaker also containing 100 ml of water. In that 50 grams of sodium chloride is there, and another stirred it, completely dissolved, and 50 grams of AgNO3, silver nitrate is also there. We can dissolve it. Afterwards, both this solution, one is a silver nitrate, another one is there sodium chloride. So afterwards, you can mix both these. Finally, one white PPT is formed. That is, we can call it as a precipitations. It is settled at the bottom. This is, we can call it as precipitation. What is that precipitation? So this AgNO3. So AgNO3 is dissolved. At the same way, Ag chloride is not dissolved. So Ag chloride is there, sodium nitrate is there. Sodium nitrate is not dissolved, that is settled at the bottom. This edge is here also dissolved. So that is, we can call it as a precipitation reaction. Like that, some dissolved salts are finally is increasing its concentration in the water after passing the critical level. It is forming into as undissolved form. The undissolved salts are collecting and adherent, heavily, hardly adherent on the inner wall of the boiler. We can call it as a scale or scaling. Suppose if it is not adherent, it is a smooth also, and it is a slimy also, smooth, slimy, not adherent or sticking on the inner wall of the boiler, that we can call it as a sludge. First one is adherent and paste, we can call it as scale. Second one is not, it is a sticking on the inner wall, that is, we can call it as a sludge. So increasing of the impurities are there in the water, that we can call it as a scale and sludge form. So this is the main problem of boiler feeding water. If any percentage of water impurities are there in the water, scale and sludge form. I think you can better clarification of any undissolved salts is sticking on the inner wall of the boiler, we can call it as scale. So without is not stick, it is smooth and slimy and floating in the water and settled at the bottom, we can call it as a sludge. That is scale and sludge as form. As the same way, in the scale and sludge, what are its contents are there? Might be it is calcium carbonate, magnesium carbonate, and including of magnesium sulfates, potassium sulfates, potassium chloride, any other dissolved salts is there, finally react with the water. For example, so it is excess of oxygen is there. Even in the purest water, excess of O2 is also there. That is, O2 is there. It is useless for us. It is affecting in the steam. If it is excess of oxygen is there, the excess of oxygen is there, react with the water along with this hot condition of the boiler walls. So it is iron is react with the oxygen and water, forming into as the body metal is ferrous hydroxide as a form. So this ferrous hydroxide again is react with the minimum supply of oxygen and N molecules of water. Water is, of course, it is there in the boiler. In that, so it is forming into as Fe2O3, NH2O. This is hydrated ferrous oxides, hydrated ferric oxides. We can call it as a rust. Even excess of oxygen is there, it is causes the rust in the boiler wall. So it is rust as formed. That is, we can call it as a corrosion. Due to this corrosion of the boiler, we can call it as a boiler corrosion. Already you know the definition. What is the define the corrosion is? The destruction or deterioration of the metals by the environment through chemical and electrochemical changes. We can call it as a metal corrosion. That is what. So as the same way it is applicable to boiler, we can call it as a boiler corrosion. You define the boiler corrosion. This the destruction or deterioration of the boiler due to the impurity waters present, due to or by impurity waters containing to producing the steam through chemical or electrochemical changes, we can call it as a boiler corrosion. If scale is there, sludge is there, it causes the corrosion. As the same way, dissolved gases are there, forming into the acids. If, for example, carbon dioxide is there, so carbon dioxide plus water, it will form the carbonic acids. That carbonic acids, due to this 100 degrees centigrade of heat, it can dissociate into this carbonates of iron. So iron carbonate is formed. So that is settled down at the at the bottom. Whether it is precipitate is attached to the wall, forming into this case.